Getting started on our next kinetics topic, it's going to seem like it's unrelated, but it's related, I promise. Going way, way back in your chemistry knowledge, when we first started writing elemental symbols, we often wrote them like this, where the X is representing the element that you're talking about. The bottom left number is the atomic number. That's the number on the periodic table. That also represents the number of protons in that element. And the top number is the mass number. That's the summation of protons and neutrons, because remember, that's the majority of mass in an atom. The reason we're talking about this is so that we can talk about nuclear chemistry, and there are various things involved in nuclear chemistry that you may or may not have seen before. They're given different symbols when you talk about nuclear chemistry. For instance, a proton in nuclear chemistry is typically represented as a symbol P, that's a lowercase p. It gets a 1 at the bottom because it's a proton, and there's a 1 up top because that's the whole mass of a proton. It is a proton. A neutron in nuclear chemistry gets a 0 at the bottom because the atomic number officially is the number of protons in the nucleus, and a neutron doesn't have any protons. So it gets a 0 down at the bottom and a 1 up top because a neutron weighs 1 AMU. An electron gets this symbol. It's sometimes represented as E. It is often represented as a beta instead. We're going to talk about things beta decay. That's beta can be an electron. A positron is another subatomic particle that gets the E or the beta symbol as well. And something with a 4-2 mass atomic number symbol is a helium atom, but nuclear chemistry will refer to it as an alpha particle most of the time. So in nuclear equations, they're different from our traditional balancing of chemical reactions, but they're not difficult. I've got faith in you. You can do this. You just have to be able to do some addition and subtraction. You must conserve mass, and you must conserve atomic number or nuclear charge. So the bottom numbers on the left-hand side, on the reactant side, must sum to the same thing that the bottom numbers on the right-hand side, the product numbers, do. Same thing for the top numbers. So on the reactant side, my sum is 92. On the product side, my sum is 92. On the reactant side, my sum of mass is 236. On the product side, my sum of mass must be 236. So it's common to be asked questions like this, where you have to identify what the unknown is on one side or the other of an equation. So if I start with mass number, that's the top number, first, what's missing on the top? How many protons and neutrons are missing? Hopefully you said 4 protons and neutrons are missing from the top. How many are missing on the bottom? 2. So a 4-2 thing is an alpha particle. So that top reaction, when polonium decays, yep, we're going to call it that. When polonium decays, it emits an alpha particle. What about when cesium decays? There's nothing missing on the mass, and there's -1 to make them both equal 55, so that counts as an electron, also known as a beta particle. So if we go through and balance all of these, making sure the reactants and the products have the same atomic symbol and mass symbol. In the top one, we eject an electron or a beta particle. That's called beta decay, beta particle emission. It's a decay because the beta particle is a product. In the next one, we're missing that thing, which is a positron. So again, it's positron decay because a positron is the product. In the next one, That's called electron capture. So could you officially write this as a beta symbol? Yes, but the way we talk about it more often is electron capture and beta decay. Why do we do it that way? I don't know. Next, we've actually already seen that one. It can be written as a helium atom or an alpha particle. That's alpha decay. Next, that's another positron decay. Next, beta decay. But look, I wrote different symbols for this beta decay and this positron decay. That's okay. A beta and an E is the same thing. In the last one, things look a little different. The mass doesn't change, the atomic number doesn't change. Yeah, we emit something called a gamma particle. That's a gamma decay. If you take a look, this little M tells me that's a metastable technetium, and that metastable technetium can decay by emitting a gamma particle. So that little M tells me a high energy gamma particle can be emitted to make regular 99 technetium. So watch out for that little M on occasion. Why does all of this nuclear stuff matter? Where is it found in the real world? It's actually very common in medicinal uses to do radioactive things. So here's a whole table from your textbook of things that are used in medicine, radioactive isotopes that are used in medicine. They're used in a lot of imaging techniques, but other things also. Why are we talking about it now when we're talking about kinetics? Well, if you notice from this row, this column of your textbook table, it tells you about the half-life. All nuclear reactions are first order decay. And so we can talk about how long a medical dosage of something, especially for imaging, we'll say, we can talk about how long that remains in someone's system by determining or by calculating, talking about the half-life. So you know if you give them a dosage of a certain amount, after how many half-lives does it take for that to be emitted from a patient's body? That was a very brief overview of nuclear chemistry and what's involved, and that's as deep as we're going. But the reason we're choosing to talk about it right now is because we're talking about kinetics, and this is the rate law for a nuclear reaction. All nuclear reactions are first order reactions. They're first order processes. One thing to note that's different about nuclear versus regular chemical kinetics that we've been discussing is this is their rate constant. It's a lambda. It gets a different symbol than we've been giving the rate constant. Rate constant is K to us. It's lambda when you're talking about nuclear reactions, but no big difference. This is the half-life equation that we have seen, but the half-life equation for what order? First order. Nuclear reactions are first order. Okay,